Hello everyone, my name is Shirin Hajahmadi and I'm a postdoctoral researcher at Lab, University of Bologna. I will present our study on the impact of voice-only and embodied conversational virtual agents on mixed reality puzzle solving. This research is collaboration between the University of Bologna and the University of Hamburg. We developed an MR application incorporating a conversational virtual agent to assist users with a 2D square piece puzzle solving task on user demand. Then we compared the impact of the representation mode of the CVA on user experience. MR environments enhance precision, coordination, and state-aware interactions, making them well suited for special problem solving and assembly tasks. Puzzle solving can be considered as a type of assembly task requiring users to recognize, position, and orient pieces with accuracy. Previous research highlights the importance of visual guidance in MR assembly tasks, particularly in object placement and alignment. Shared virtual experiences and collaborative problem solving have been widely explored in puzzle solving tasks, involving both human-to-human and human-to-CVA interactions. Conversational virtual agents have been extensively used in education, healthcare, and service applications. Some interesting studies have investigated the role of CVAs in XR puzzle solving. Also, research highlights the impact of CVA's realism and interaction modes. Now let's discuss how conversational virtual agents can be categorized based on key attributes. CVAs can be classified along three main dimensions. First, purpose. CVAs are typically task-oriented, meaning they are designed to assist with specific activities, like guiding users through a puzzle-solving task. Second, communication channels. These agents can be text-based, voice-only, or embodied with a visual representation. Third, response generation. CVAs may rely on different response mechanisms. Rule-based systems follow predefined logic for consistent and structured responses. Retrieval-based models select responses dynamically from a set of pre-generated options. And AI-driven models, leveraging machine learning and natural language processing, generate more flexible and natural interactions. In addition to our previous classification, another important framework for categorizing conversational virtual agents is the Miras-Cube taxonomy. This model evaluates CVAs across three key dimensions, helping us to understand their role in interactive systems. First, corporeal presence. This defines where the agent exists, purely virtual, purely physical, or somewhere in between. Second, interactive capacity. This measures how well an agent maintains engagement by providing context-aware and frequent responses. Third, agency level. This describes how much autonomy the agent has. CVAs can range from weak, with rule-based responses, to strong, with adaptive learning behaviors. Our research focuses on how MR and CVAs enhance special problem solving. MR in a special task improves precision, coordination, and spatial awareness, making it ideal for puzzle solving. Visual guidance aids users through step-by-step overlays, but its effectiveness and potential overload needs further study. CVAs in XR and puzzles enhance engagement, but their representation, their dialogue with the user, and voice-driven interactions remain underexplored. On-demand assistance impact performance, workload, and social dynamics, requiring deeper investigation. Building on these points, our study compared voice-only and embodied CVAs, analyzing how their presence and guidance style affect performance, interactions, and workload. Based on this background, our study explores three key questions. How does the CVA type, voice-only versus embodied, affect puzzle-solving performance and user interactions during a 2D spatial puzzle-solving task in an MR environment? What is the impact of CVA representation on cognitive workload and social presence? How do participants perceive the usability and acceptance of the MR system? Our system was built in Unity 3D and deployed on Microsoft HoloLens 2. We used MRTK for hand gestures, voice commands, and spatial mapping, and Vuforia SDK for precise puzzle tracking. In our application, users issue voice commands for feedback on piece position or orientation. The CVA confirms or provides directional guidance. Based on classification frameworks, the voice-only CVA has low corporal presence, while the embodied CVA has high corporal presence. Both maintain high interactivity with real-time context-aware responses. They are task-oriented for puzzle assembly but weak agents, relying on rule-based, on-demand interactions. Let's walk through how our system works, from user interaction to CVA assistance. Imagine a user engaging with our MR puzzle-solving task. They interact in two ways, using pin gestures to move pieces or voice commands to request guidance. As they begin, the gesture recognizer detects their pinch inputs, allowing them to grab and position pieces. Simultaneously, the custom switch input processes voice commands, such as asking for correct placement. The piece state manager tracks each piece's position and orientation in real time. Behind the scenes, the system processes these interactions through the puzzle manager. The puzzle initiator sets up the board and in the embodied CVA mode positions the virtual agent. The puzzle state manager monitors progress, ensuring the correct placement of pieces. The puzzle state validator checks accuracy, providing instant feedback when piece is correctly or incorrectly placed. When a user asks for help, the system responds dynamically. The response setter processes queries, determining whether user needs positioning or orientation assistance. Real-time voice and visual feedback is then generated to guide them. Finally, the data logger continuously records interactions, helping us to analyze user behavior and refine system performance. Before the main study, we conducted a pilot study with 16 participants, leading to system refinements such as memory optimization to prevent crashes, gesture training to ensure smoother interactions, simplified voice commands for better speech recognition, and improved avatar placement to enhance visibility and social presence. The main study involved 34 participants, randomly assigned to either voice-only or embodied CVA conditions. The procedure included first, briefing and consent, second, demographic questionnaire, next, familiarization phase, next, puzzle-solving task, and at the end, post-task questionnaire. We analyzed objective and subjective metrics, completion time, accuracy, and interaction types for performance, social presence, usability, cognitive workload, and technology acceptance through validated scales. Voice-only CVA improved task performance, leading to faster completion times and higher accuracy than embodied CVA. Users needed more assistance for positioning pieces than for rotating them. Both CVAs resulted in similar interaction frequency, with users making comparable numbers of position and orientation related queries. No significant advantage of the embodied CVA for social presence, usability, or workload. Embodied CVA increased cognitive effort, likely due to processing both visual and auditory inputs. Both CVAs showed comparable usability, message clarity, and perceived usefulness. Users asked more questions about positioning than orientation in both conditions. Position-related queries peaked early, then gradually decreased as participants gained confidence. By the final stage, almost no queries were made, showing that users had resolved most uncertainties. Let's briefly discuss our key findings. The voice-only CVA led to faster completion and higher accuracy, reducing cognitive distractions. Users struggled more with positioning than orientation, with most queries happening early. While CVAs continued to help throughout, uncertainties decreased over time, indicating users relied less on guidance as they progressed. The embodied CVA increased cognitive effort but didn't improve social presence, suggesting that for task-focused problem-solving, embodiment may not be necessary. Both CVAs were effective, but visual embodiment didn't enhance usability or acceptance. This highlights the need to prioritize auditory guidance for high-focus tasks. Future work of our study could include exploring more expressive avatars for increased co-presence, analyzing how embodied CVAs affect social inhibition and accuracy, and implementing more detailed real-time adaptive feedback. Thank you for your time and attention.